Hello and welcome to this video series. I am Akram Ahmed, and in this video we will look at graph theory. Okay, so let's start. So first of all, let us define what is a graph. Well, formally speaking, a graph is a mathematical model that formally represents a collection of objects that are all interconnected. Okay, so some of them might be connected with each other, some of them might not be connected. The type of connection between them is shown. So this is an example on the right over here where you could see a graph where you have different objects which are represented as color nodes over here, or the circles over here, and they are connected to each other in certain fashion. Okay, so this green is connected to this red, and this blue, and this red, but this green is not connected directly to this blue, so it is showing you where the connections are happening. And this is actually quite useful in many applications such as maps, websites, communication networks, electric circuits, programming circuits, and all other type of things. Okay, so in computer science we actually use it a lot to represent multiple things, and we'll see an example where the abstraction is going to take you to a graph, and then you can actually solve problems using the graphs. So here is a problem. Let's look at it in details. So it basically is a maze. So we're saying Ahmed wants to play a maze game, and the maze game is made of square rooms where each side of the square has a door that can either be locked or open. Okay, so this is a maze. You can enter a room, and in that room you'll have doors on all walls. It's a square room, so you enter it from one, so you will have 3 more doors in front of you, one in the right, one in the left, one in front of you exactly, and some of them might be open and some of them might be locked. When Ahmed starts, he has no information about which door is open or how many rooms are there, so he doesn't know any information about how many rooms are there and which door in each room, the status of it. Is it closed or is it open? Okay, is it locked or not? Since Ahmed cannot open the lock doors in the game, what we want to do is, as a first step, we want to construct a graph for this problem, and then we'd like to drive a tree from that. Okay, so we'll talk about the graph, and then we're going to talk about a tree. As you can see on the right over here, this is a picture, and it mimics what the problem is looking like. So there are some doors that are open, some doors that are closed, and you can see some closed doors, and you will have to navigate somehow to go from one room to another. And usually what the maze has is you start from a room and there is a target room, for example over here, and then you have to follow the open doors to go to it, and you might have more than one path. Okay, so this is just an example, and to make the idea more clear, what we are trying to do, let's take this search problem. So suppose that you are searching for something and you have these room connections, and you start from a source which is labeled as room S, and you want to go to a goal which is labeled as G. So this is the goal room that you want to go to. Okay, and what we want to do is we have connections to other rooms. So there are some paths that lead to a dead end. For example, if you go like this, this is a dead end. And there are some paths, the multiple paths that you can actually take to go to the goal. And we'd like to represent this information in graph theory. So these rooms then can be abstracted to a graph, and we'd like to see how we can abstract this information to graphs. Okay, so the best representation for this is something called a graph, and what we will do is that when Ahmed starts, each room that he visits, he's going to be denoting it as a node, and we will represent that as a circle. Okay, so we want to create this map but in a graph fashion. Okay, so here's what we do. Let us use the following representation. Each room Ahmed enters by is going to be labeled by a circle, and in that circle I'm going to put a letter that will copy the same room that he is in. So if he starts at S, I'm going to put a circle and put an S in it. If he's room E, I'm going to put a circle and put an E in it. Okay? If there is a door to an adjacent room, that is open actually, we put a line indicating an open door to that room. So for example, you go to S, there are two open rooms, so we will put a node A and then we'll put a line between them as we go. So this is what we're going to do. So let's start doing this step by step. So here we go. Ahmed has started. He is in the first room. So we are going to go and draw something like an S over here. Afterwards, we are going to look at the doors that are open. So there are two open doors, one on the right, one in the front or top. We don't care where the doors are, but what we know is, by fact is, that there is a connection between S and A because this door is open. So I am going to go and draw a line to A and a line to B. So I can actually go from S to room A and I can go from S to room B. Okay? And that's a choice that I'll have in the future. Then what we do is we have to move to one of these rooms and we will go by lexical order or by taking A. So we go to room A, and when we go to room A, we will see that there are doors open to room D and room B. Okay? So again, by using the lexical order, we will make a room D and a room B, a line to room B and a line to room D, and A will be connected to A, B, D, and notice the S, the door is over there, that connection was already there, so this is basically representing exactly the case that is over here. Then we have to move to one of these rooms, and since we are going in lexical order, we'll go to B, and then from B we will go and we will see a door that is open to room C. So basically we'll go and draw a line to C, then we'll move to door C, okay, and then when we go to door C, to room C, sorry, so we will see that there is a door open to room E and we can draw to room E, and when we go to room E we reach to a dead end. Okay, and when we reach to a dead end, we retrace our foots back and go to a room that was not fully explored. And as you can see over here, we explored S, we explored A, we explored B, we explored C and E, but we did not explore D, so we will go back to C, B, A, and then go back to D, and we will explore D now, okay? When we explore D, we have a door open that is going from D to the goal, okay, G, and we can draw a line connecting G. Now, very important thing in the graph is it might not be representing the exact physical layout. So notice G is on the top, whereas G is on the bottom of the room. So it might be representing physically what's going on, and it might be not representing what's going on. The important thing is the connection between the rooms, and the labels have to be correct. So if I'm at S, I can go at A no matter where this S is. Okay, so that from D I can go to G, and that is actually going down by this door. Okay, so the representation or the location of the node has no relevance to the actual physical location. Okay, and the actual relevance is I can go to it using this line. Okay, and we call this line the edge. Okay, so there is an edge connecting D and E if there is a door open. That is what we formally say. Okay, so we have nodes and we have edges. Okay, so this graph is now representing these rooms and how I can move into them. So I can, if I'm in room C, I can go to E and B. You can see it from the graph, and it's the same thing over here. From C I can go to E and B. If I'm at room D, I can go to G and A. So if I'm at room D, I can go to G and A. Notice it is representing the same information, but in a different and abstract manner. Instead of thinking of rooms, now we're thinking of nodes and edges. Okay, so there are no other doors in room G, and we reached another dead end, and we have explored all rooms, so my graph is complete now. So I have the full graph of my problem, and I can start representing the information into it. Okay, so graphs are basically a very powerful type of representation that computer scientists actually use, and in each circle is called a node or a vertex, and the line connecting two vertices or two nodes is called an edge. The starting node has a special name called the root. So this is the node that we start from, S, that will become the root. This is where we started from, and when we start to explore, that will become our first node. So that's the root. And there are something called the leaf nodes, and the leaf nodes are the nodes where we reach to a dead end. So there is no other connection edge going out of it to another room. Okay, so in that case, E is an edge and G is a leaf node. Okay, so this is a leaf node, and these two are E and G are leaf nodes, whereas D is not a leaf node, because when you go from A to D you can go to G, and when you go from G to D you can go to A. So it's not the leaf node, it's actually G and E. These are the only leaf nodes. Now, although this is a powerful structure, and if we are talking about search problems where you want to search, one thing that we would like to avoid is having loops. And notice over here, from SABS, this is creating a loop. So if a computer agent is trying to actually do a search, and it happens that is always selecting SABS, then ABS, then ABS, it is going to go into a loop over here, and it's not going to ever find the goal that is over here. So it'll keep on going onto loop. Okay, and this is why when we are doing search, we do not like to have these loops, okay, inside the graph. To avoid the loops in the graph, what we do is we convert the graph into a tree. Okay, so when we're talking about search, we always construct like a tree from a graph, and that tree will not have this loop. Okay, and what we do basically is when we're constructing a tree, we take the graph itself and we start from the root node and we put it on top, and then we look at its children. Okay, so these are called the children. So this A is a child of S and B is a child of S, because you can go from S to B. So this is a child and a child, and then we have two, A and B, and we have to put them under the S. So we say we can go from S, from A to B. And notice over here, I always put A on the left hand side and the B on the right hand side. Okay, it's basically on lexical order, so any letter that is prior in the alphabet will go on the left, and any letter that is later on the alphabet will go on the right. And this is just a convention that people go by called the lexical order, and this is how we arrange it. So we can go from S to A, from S to B, and then what we do is we will explore A. So we'll go to A and explore it. So we go from S to A and we're going to explore the A. So when we go from S to A, notice I only have two paths that I can actually choose. Since I came from S to A, I'm not going to go back on the same path. I have to move forward, so I only have two choices that I can do. I can either go to B or I can go to D. And using the lexical order, B is going to go on the left and D is going to go on the right. Okay, so this is what's going to happen over here, and A is going to branch into two children nodes, which is B and D, and then we will move to B. Now notice I came from S, A to B. How many children will B have? Well, ideally speaking, you might say that the S is a child of B, but since we are avoiding loops, we will stop this and we'll say we'll not go back, because this is going to create a loop for us. So we will go from S, A, B. There is only one child that I can have, which is C. Okay, so that is why we have only one child over here, and from C we can only go, we're not going to go back, we're going to only go to one direction, and then we're going to go to E, and at E, since it's a leaf node, there is nowhere to go. This is where the tree stops. Okay, so this is one branch of the tree. It starts from S, goes to A, B, C, E, so it's S, A, B, C, E. Notice this is one branch. There is no loop in it now. Then the SA, we can go and explore the D now. So SAD, when you go to SAD, D has one child, and that is Chi. So we can add that into the list of the tree. So I can go SADG, that is another branch, SADG. Now on the right hand side you have S, and the S can go to B, so we are starting from here and we're going here. So this is one branch, And from B, you have two doors actually open, so it is basically C, or you have two edges. So the two edges are C and A, and for lexical order, we'll put A before, and then we'll put C. So from S, when you start, you can go to B, and then from B, you can go to A, and from B, you can go to C. Notice in this branch, whether you go here or there is no loop. Do not confuse different branches. So different branches might have different paths, but they will not have, each branch will not have a loop. And hence SAB, so going from SAB, notice over here, this is not having a loop. Okay, just to clarify this information, notice the path that is over here, I'm just going to draw it over here, SABCE, it is this path, SABCE, okay? And coming over here, let me change the color. Let's take a dark blue color. And this path, SB, so SBA, it's basically the path SBA. There are no loops between, the red one has no loop and the blue one until now has no loop. Okay, so that's the SBA, and it's going to continue from A. Now from A, I will not go back to S because I don't want a path that bites itself, as they say. It doesn't go back to the same state that you were in previously. So you will go to D from A you will go to D, and then from D you will go to G. So notice the SBA's DG, this is a new path that you have. Okay, this is a branch that was not there before. Now the last one is the SBC, so now you have the SBC, and the SBC will basically go to E. Notice we have explored all branches. So there is a branch that goes like this, there's a branch that goes like this, there's a branch that goes like this, there's a branch that goes like this. Okay, these are all the possible ways that we can go, and the tree basically tells you all of this and represents it in a very nice manner. Okay, so you could actually construct a tree, and this tree now has no loop. So once you go down a tree doing a search, okay, you are sure that there are no loops that you will face, and you will go in circles and not reach the target. Okay, and that is why we construct from a graph a tree. Okay, so this was an example. So we converted this maze problem into this graph problem, and from the graph problem we actually made a tree. So equivalently, this maze problem is equivalent of solving this tree. So I want to start from S, and I want to find something in G, so I have to look at where G is, and once I look at where G is, I get to know, oh, I have two paths to G, and you can actually see the path to G. Okay, so as intelligent human beings, we can look at these trees and we can come up with a solution. Now, how do we represent these trees into a programming language? Okay, so this is basically a very simple code. This is a Python code actually. And in this Python code, what we're trying to do is we're importing something called network X as NX. So this is a library, and this library makes you draw the network that you are drawing, so you can actually make a graph in it. Okay, and I'm also importing over here matplot library. Okay, so it's basically library that helps you in plotting things in Python. And what I'm doing is I'm saying G is NX, and NX is nothing but a network library dot graph. So I am actually asking it to make G my graph. Okay, so G is a graph now, and in the graph I can do a G dot add node. So this is a add node from. This is a method that actually is in the graph element, or the graph class, or the object, and I say, well, there are these many nodes in the graph. So I state all the nodes. Now notice over here, if I go back to our example, okay, and we go back to our graph, let's go back to this graph. In this graph, we have to state all the nodes. So we have S, A, B, C, D, E, G. So we go over here, and notice over here, S, A, B, C, D, E, G. All the nodes are listed over here. So I tell this graph that, hey, these are the nodes that you have. Okay, so they have to be between single quotes because they are nodes. And then we add edges. Okay, so we say that there. How do we add edges? We say g.add edge from, and then between brackets we give it, hey, you have an edge from S to A. And notice again, there is an edge from S to A. This is the edge. There is an edge from S to B. Okay, and we go over here and notice the edge from S to B, and then there is an edge from A to B. Okay, and there's an edge from B to C. Okay, so we're still halfway through the graph until now, from A to B, B to C. This is what we added till now. Okay, and then we come, there's another line over here, we're adding an edge, which is CE. Okay, so we can go over here and say, hey, this is an edge that's there, and then we are coming AD. Okay, so that's an AD, that's an edge over here, and lastly we have the edge DG, and over here this is the edge that we have. So we identified all the nodes and we identified all the edges for this graph. Then I'm actually asking it to draw the graph for me. Okay, so when I do this and I run this code, notice this is a figure that has been placed. This is a graph. It's the same graph that we have. Okay, notice it's S going to A, D, and G, and then S, B, C, and E, and there is a connection between A and B. And whenever you draw a graph, you can have it in any way. As I told you, it doesn't have to represent anything. The graph could be drawn anyway. What it means that there is a connection. And what does this edge mean? It means, in our example of the doors, it means that we have an open door between A and S. Okay, and it can actually represent anything else, and that's why we call this as an abstraction method, where we abstract the problem and draw the graph, and then we can actually solve the problem on the graph. And when we solve the problem on the graph, we are actually solving the problem within the actual problem that was the maze in the room. Okay, so this is how we represent the graphs, and we're going to be utilizing this in the next videos, where we're going to be talking about breadth first search and depth first search and all that other type of search. We'll be talking about these graphs, so please go ahead and make yourself familiar with this graph, and then I'll see you in the next video where we're going to talk about search strategies, and we're going to be talking about breadth first and depth first search. Thank you for watching. Bye bye.